Okay, so please all welcome to our first talk here. That's my first Go project from Thomas. And yeah, Thomas is next to Go coder, an anarchist, a Bostonian coder, Devout believer in uncertainty, drinker of wine, eater of fruit, hater of cats, musician, and sorter. So yeah, have fun and please start.
All right, thank you. Yeah, so I'm like the announcement for the meetup said, it's going to be nerdy. I'm going to be talking about things like compilers, Lisp, tail recursion, and if at all you get confused and you need something clarified, please stop me. I have no problem being interrupted and then just picking up where I left off. So a little bit about me. My name is Thomas Bradford. I am from the US. I've been in Berlin for about 10 years at this point. It's starting to grow on me. I've been developing software for almost 35 years now, so the majority of my life. I used to write database internals back in the 2000s as an actual job. These days, I design programming languages and compilers as a hobby, and we'll talk about that. About 4 years ago, I decided to learn Go, and they still haven't fixed error handling. So I want to talk about why I would choose Go, because everybody has their reasons. And for me, the first one is that I'm actually of the old school. My first languages were Pascal and C. And so for me, the syntax of those languages somehow are familiar to me. And languages with a lot of syntactic constructs tend to confuse me. I like my code to be fast, but it shouldn't cost too much, meaning that there shouldn't be a cost to actually managing memory, an accidental cost that makes it really hard to produce value. And so for me, Go sort of strikes the right balance in that sense. Not a big fan of threads. I've had my fill of battling them and debugging them. And for me, Go's concurrency model is vastly superior to just straight up threads. And also, I suffer from rhabdophobia. If you don't know what rhabdophobia is, it's a fear of magic. And when I say magic, I mean, I don't like languages that do magical things. A good example would be Ruby. So Ruby has a concept called method missing, where if you make a call and the method doesn't exist, Ruby will figure out what it can do in order to satisfy you. And this creates a situation where you're dealing with runtime problems that you're having to debug, and you don't really know what the language is giving you. And this is partly why I like Go. I think for me, the most magical thing about Go is probably the range operator. So looping over either a channel or an array or a slice. That's the extent of the magic that I've seen in Go, and that satisfies me pretty deeply. Rhabdophobia is also the fear of being beaten with a stick, which is how I feel when I have to code in Ruby. So I want to talk about my first Go project, and I just want to let you know I don't go with Hello World, and I'm not of the opinion that people should go with Hello World as their first project, because it's really not teaching you much about the language, right? You're getting a little bit of syntax. You're understanding kind of how modules are laid out and imported, but really you don't get a good taste of Go from that. You might do something a little more complicated, right? You might make a channel and then pull world back in from a channel and then print it out, but that still really isn't stretching the language and giving you a good feel for it. So my first Go project started out like this. If you've been in the Go community for a while, you might actually know this code. Can anyone guess what it is? Does anybody want to try?
It's a lexer.
Absolutely, yes. It is stating the obvious. Yeah, it actually is. It's a Rob Pike lexer. So he gave a talk on YouTube several years ago about how to create a lexer using channels in Go, where you took a very push approach to creating a lexer, and then you just jam the tokens into a channel so that some other Go routine could start pulling them out and iterating over them. And for me, that was the thing that made me say, wow, Go is actually an interesting language, because you can still approach solving problems in this traditional kind of imperative push way, but you have some of the benefits of sort of a delayed consumption of information, which is great, without a lot of the accidental complexity related to like threading and synchronization and so on. So this is what it started out looking like. It ended up looking like this. This is my count of lines of code for the project. And you can see there are about 9,800 lines of code in Go. There's a bunch of markdown. That's not important. There are about 844 lines of scheme. And you might be wondering, okay, well, what the hell is that? And I'll explain. So I built a scheme compiler as my first project. Thank you for the link. I actually have the link in the slides too, and I'll share that later on as well. I go big on my first project in a new language. The Kubernetes team also went big on their first project in a new language, right? They were Java programmers, and they decided this was going to be their first Go project, writing Kubernetes or rewriting it. And that's why you have factories everywhere. And I made a lot of the same kind of mistakes, and I'll talk about that. And I think everybody should go big, to be honest. So let me talk about Scheme real quick. If you've never heard of it, I'll breeze through this just so you can get a kind of a feeling for the language. It's a Lisp dialect. I'm sure people are familiar with Lisp. Not many people have developed a love for Lisp, not the way that I have, at least. Lisp is a symbolic programming language, and that's kind of hard to explain. But basically what it means is that it's capable of manipulating its code as easily as data. Writing an embedded system, yes. So, and this is something novel in programming languages at the time that Lisp was created, that symbolic information could be manipulated. And one of the great unique selling points of Lisp when it was invented, and it was invented by John McCarthy, is that because a Lisp program could write Lisp programs, you actually had the foundations for artificial intelligence. And you might know that John McCarthy, the inventor of Lisp, also coined the term artificial intelligence. So early on, Lisp was all about AI. It hasn't really taken hold. People prefer Python, but it all started here. And it actually started quite a long time ago. Scheme is a dialect of Lisp. It was invented in 1975 by Guy Steele and Jerry Sussman at MIT. And that was within my life at the time. So now you can kind of get an idea of how old I am. And in case you didn't know what they look like, this is what they look like. Is anybody gasping? Yeah. So you might be saying, okay, that's a lot of parentheses. How can I deal with that? And the way to do that is with a 1970s Lisp keyboard. This is how you would type Lisp back in the 1970s. So here's how I started off. I do have to explain that it started off with the Rob Pike lexer, but it really doesn't resemble that in any way. And the reason for that is because it's a compiler at the end of the day. And a lexer is really just one part of a compiler. And this is what a compiler pipeline looks like. And I'll briefly kind of explain the steps of a compiler for those of you who don't know. And I love Emacs, by the way. Yes, thank you. Emacs is written in Lisp. It's common Lisp, but it's still a Lisp. So the first step is this lexer, and that's the lexical analysis step. And the idea there is that you're scanning the input stream for the sort of the landmark characters of the language, like open parentheses, close parentheses, the numbers, identifiers. They don't have any contextual relevance at that point. They're just a stream of distinct tokens. Next step would be syntax analysis. Do these tokens, one after the other, do they make sense as far as the language is concerned? Are they valid? When you open a list, do you close the list? And do you nest it properly? This is the syntax analysis step of a compiler. Next would be semantic analysis. And what that basically means is that if you see identifiers or if you see constants like numbers, do they make sense where they are inside of the grammar that's been produced? Meaning, has that identifier even been introduced and created and bound or defined right? Those are important, and that's one of the major steps of building a compiler. Next will be an intermediate code generator. This is like an IR. So LLVM is kind of based on this idea, is that what you're doing is manipulating an abstract version of what is kind of close to machine code, but not quite. But it gives you the ability to actually move things around and make changes to the underlying abstract representation more effectively than if you were dealing with an abstract syntax tree, which is what a syntax analyzer would actually produce. Finally, there's the code optimizer. This is the thing that's removing dead code. It's creating local and global optimizations and rewriting that intermediate representation. And then the last step would be to emit a final set of machine code. And that could be for a real machine, like an Intel processor, or it could be for a virtual machine, like the JVM. These are essentially the steps. So what complicates that is Lisp is weird. The way that it breaks its compilation pipeline down is into two steps. And the first one is called reading. Reading is the first two steps. That's the lexical and the syntactic analysis, meaning it's getting all of the structure of what it's reading from the stream, and now it can represent that stuff as data. That's the kind of the important thing about Lisp, is that the code is actually data. And there's a nice side effect of that, and that is that you can take data and treat it as if it's code. The next step is to take that data and actually treat it as code. And that means you pass it into an evaluator, the eval function. And that's performing the rest of the steps, depending on the version of Lisp that you're using. It's actually taking the data and doing semantic analysis and compiling it down to some sort of runnable format. How it reads. The good thing about these steps is that they're actually first class in the language, meaning that you can call them yourselves, right? It's not a situation where there's this standalone compiler and you compile stuff and it produces machine code. It's actually an environment where those functions exist within the environment, and you can feed them textual data and get data structures out of them. And then you can feed stuff to the evaluator and get runnable code out of it as well. They're available to you, like I said. In most Lisps, it's going to be generally actual lists. In the case of what I'm producing in my reader, it's a sequence. And if you've ever used Clojure, I don't know how many people have. Clojure uses sequences extensively as kind of a boiled down interface. And I did sort of the same thing with my implementation. So Rob Pike's lexer is not there anymore. It wasn't up to the challenge of the type of stuff that I was trying to do from the point of view of implementing read as a first-class function. Reading looks like this. You call read and you give it an input stream. And in this case, the input stream is just iterating over a string. But it could be any input stream at that point. And it'll evaluate to this. Display hello is a list. And it contains two elements. The first one is the word display, which is a symbol. It's actually an identifier that can be passed around. And the second element is a string, the string hello. Now that on its own doesn't do anything, it's just a list, it's a piece of data. Evaluation is the next step, right? That's all of the rest of it, taking that data and compiling it into runnable code. Also available to the programmer, and this is where Lisp gets this property of being able to write Lisp code, because you can create data that actually becomes programs and then create more, those can create their own programs, which is rather interesting. Dangerous in JavaScript, but not necessarily in Lisp. So this is evaluating in Scheme. And what you can see is that all I did was pass that same call to the eval function. So the result of read is just passed into eval. And there you have sort of the complete pipeline implemented, the ability to display hello onto the screen. You can also synthesize the list. So this is what I mean by just taking any arbitrary data and passing it in to the eval function. And in this case, this is just a quoted S expression in Lisp. So it's treated as a literal list with a symbol and with a string. But you could also do it like this, which is, oh, sorry, that's the cons. Yeah, this is the literal format. So back to my first project. How how am I doing on time? I'm totally keeping up. That's good. The name of the project is called Ale. It stands for a Lisp environment because I'm that old that I need to have recursive naming in my projects. It is a Lisp 1 environment, and that's important because there are two kinds of Lisps. A Lisp 2 is an environment where functions have their own dedicated namespace from local variables and other variables, in fact. Lisp 1 has just one big namespace for all of them, which means you can create conflicts. But the good thing about that is that you don't have to do anything to explicitly identify a function for execution. And you might have noticed that when you use Emacs, for example, because Emacs is a Lisp 2. It's borrowing pretty heavily from Scheme and Clojure, but mostly Scheme. It generates abstract machine code. And this is what I mean by that last targeting step. And it's meant to be hosted in a Go process. And more specifically, is meant to be isolated inside of a Go process. So you can create multiple environments, and they don't share data of any kind, which is great because then you could use them to run some sort of scripting process and then just discard them through the garbage collector. Do I want you to use it? I'm not selling anything here. I don't want you to use my Lisp environment. It's okay. The short answer is no. If you're interested, that's great. The long answer is that I have a deep love and passion for Lisp, which might make me insane, but I want to share that with you, and I would really be happy if it helped you to develop some kind of minimal love for Lisp as a result. So the approach. My approach is always agile. So I don't approach any code with a grand up, like a upfront vision for how I'm going to implement things. I will start to vertically slice things out and sort of incrementally build things out until I have something that works. And I try to have, minimally working system throughout that provides some sort of demonstrable value or change to the behavior. The first MVP was a pure interpreter, and it was really, really slow. And what I mean by interpreter is basically this. So you take those first two steps of the compilation pipeline, but you ignore the last four altogether because an interpreter doesn't really care about any of that stuff. What it does instead is mine at least, took this abstract syntax tree that I generated and then basically brute forced over the results to determine what it should do about them. So it was like a big case statement based on what it was seeing in the data values that it was getting. And it was accumulating state over time. So super, super slow. I would never actually use that for any kind of production system. But the good thing about it is that it allowed me to use that as sort of a flywheel for the further development of the language itself. So also the initial cut of the Lisp runtime, I wrote that almost entirely in Go. So all of the basic functionality that you would get from it, like sort of map reduce, things that are common functions for iterating over data sets and transforming data sets, I didn't write those in Lisp at all. They were actually Go functions for quite a while, because there were certain things at the core language that needed to be there before I could really start to implement that stuff in Lisp itself. Once I introduced lambdas and macros, and if anybody's confused about what a lambda is, it's basically just an anonymous Go function. Let's call it that. Once I introduced those, the Go code could start to disappear, right? So the Go code started to go away and slowly was replaced by Scheme code. I eventually wrote an abstract machine and a proper compiler for it. And there's a difference between an abstract machine and a virtual machine. So a virtual machine is more generic. It tries to act like a real machine with all of the same kinds of instructions that are very basal. Whereas an abstract machine has instructions that are specifically designed for the language that is being targeted, or the language that will target it. So there are a lot of instructions in my abstract machine for manipulating lists, because that's what Lisp is. It's basically a list manipulation language, and that stuff has to be fast. So at its core, there's a lot of stuff that's specific to that you wouldn't find in other machines. And then finally, I topped that off with a code optimizer. That's that second from last step, take code and make it faster. And this sort of culminated in a tail call optimizer. And this is where I'm probably going to lose a lot of people. So I'm going to try to explain tail calls as simply as I possibly can. When you are running a program and you invoke a function, what you're creating in memory is what's called a stack frame. So there's a stack and you're pushing a frame of memory onto the stack. You'll have encountered these when you have functions that are calling each other crazily in Go, and you eventually get a stack overflow and everything explodes, right? So that's basically what I mean by stack. So as you're calling functions, you're basically pushing stacks onto stack frames onto the stack. And eventually, if these are sufficiently recursive, if they're self-recursive, which happens a lot in Lisp and other functional languages, because you might be reducing with the same function over and over and over again, you're eventually going to blow out your stack and run out of memory, and you won't be able to do that kind of computation. So in functional languages like Lisp, it's really, really important that you manage the stack well. That's the top of the stack. When the function exits, you start popping those frames back off the stack, and the stack gets smaller. That's kind of the idea. Now, with a tail call optimization, the idea there is that a functional language has, at the end of all of its conditional branching, if it calls another function and is immediately returning the value from that function, then it's nominated for a special kind of optimization. And I'll kind of show you what that means. You're pushing a stack frame, you're pushing a stack frame. And then you might hit the fourth function call, and it's invoking a function like define 2.0. What you'll see here is that 2.0 is actually calling itself in a couple of the branches, right? So based on these conditions, which are bogus, by the way, this is a totally bogus function. It's actually calling itself. And where this is, as far as the code is concerned, is in the tail position, meaning is it's immediately returning the result of calling itself, or even another function for that matter. And the optimization there is actually interesting, because what it can do is it could just completely reuse the current stack frame. It could just basically reassign the argument values and then jump to the beginning of the new function just using the current stack frame, and just blow away whatever was there. And then you don't incur this additional stack frame pushing by having a recursive function. So it'll just keep calling itself until it's done. That's essentially the idea of tail call optimization. For me, that was a super hack. It was really hard. I've actually never implemented it before, and I still have to clean it up. But it's one of my most proudest moments in life that I actually got that to work. But mistakes were made. Like every new project, you're going to come in with a lot of assumptions about how things should be done. And my background was coming from TypeScript for web development and also server-side development. And then long before that, Java and Python. So I came in with baggage, and that baggage didn't help me out early. Give Go's type system. And if you're not new to Go, then you understand after a little while that there's a lot of stuff that you have to sort of grok before you really appreciate it. And at the beginning, you're just doing everything wrong. So I was creating type hierarchies instead of using duck typing, right? So instead of creating simple kind of like capability-based interfaces like closer and stringer and stuff like that, I was creating really, really complicated interfaces that built on top of each other, which made for a mess of code, and it actually made it really, really hard to refactor. This is one of the big lessons that I learned in Go, is that the easier it is, or the more decomposed your interfaces are and disconnected they are from each other. And if you're really just talking about a capability that a class provides, then it's better to not glom them all together. I was also failing to properly compose interfaces and structs. I didn't know that you could embed an interface at the beginning of another interface, or a struct type at the beginning of a struct, or even an interface at the beginning of a struct. I didn't know that you could actually do that. And so I was creating all of this sort of adapter code to sort of compose stuff together, and it was just a huge mess. And again, really, really hard to refactor. I used interface way too much. This might be one of the bad habits that I picked up early on in TypeScript, because there's an any type in TypeScript, and you're also not supposed to use it, but I used it liberally. And I started to do that pretty early on in Go, and especially for my first project because it's a dynamic language and you want to pass things around. And so for me, the empty interface was the way to do it, and I've since fixed that. Boxing primitives, I didn't know you could do that, that you didn't have to do that. So by boxing primitives, this is kind of what I mean. I had an interface called number, and it had some capabilities like comparison, add, and so on. And then I would create a struct type called integer with a value of int64 embedded inside of it. Because I didn't know you could attach methods to any type in Go, because other languages don't do that. Do I use frame pointers? Not in this abstract machine. We could talk about that later. I'm actually creating real Go functions, and I allow Go to do the work. So the early version of the code, I don't know if you can see my mouse, but the early version of the code would have, me drilling into a value to get the value out of it and then to do the comparison, right? And this made for, I wouldn't say it's super slow. It would be negligible. You wouldn't even notice it. But from the point of view of the purity of the code, it was ugly and completely unnecessary. So the newer version of it actually looks like this, because you can do that in Go. And that's something that I did not know. I love to panic and rescue. Coming from the Java world, for me, exceptions are an up the stack messaging system, basically, and for me, a controlled catch of an exception was a perfectly valid way to tell something up the stack about something that had happened that was exceptional, except when Go routines are involved, and then you can't do that. So I had to wean myself out of that behavior, and I stuttered a lot. If you know Go, then you know what this means. Basically, I would have code like sequence to vector, which that's how you read it out, sequence to vector. So you're basically saying the same word twice for no real reason. This is better, right? Sequence to vector makes a hell of a lot of sense. I also took the idiomatic guidelines on local variable naming way too seriously. And here's where I'm going to create some controversy, because the Go authors tell you just name everything with one letter if it's a local variable or if it's pretty close to the place where it was actually declared. And I did do that early on, but I've since kind of decided that I don't care what the Go authors say about that stuff. I really, for me, being able to scan forward and not have to hop back has some intrinsic value, and I really like to have real names. They're not huge Java names, but they're names, right? A good example would be this function where you have, read from string. It returns a local variable called R. Well, what the hell does R mean? It doesn't mean anything, right? It could have meant the thing that was read. It could have also meant foo. At that point, it's really hard to come back to your code and really understand what was meant. And so I tend to eschew that approach at these days. I used unqualified imports way more than I should have. And you may not even know about them because they're not taught. Nobody really talks about them. But basically, this is an unqualified import, the dot. And what that is doing is it's basically doing the same thing as a Java import some package.star. So it's taking every symbol from that namespace and embedding it directly into your current namespace. It's just copying it in, which makes for a lot of confusion, right? So you see here sequence to vector, right? This is something where if I wanted to make changes to this code without relying heavily on refactoring tools and an IDE, which I prefer to not do. I love sort of old school coding where I'm not relying on like Golang to do the refactoring for me. This would be a really hard refactoring to do because for me, I don't necessarily know where sequence to vector comes from. It could come from anywhere if I have more than one of those. The only thing I can assume is that there's one unqualified import and it must be coming from there. So generally it's better, to qualify, but then you have the stuttering problem, and of course you've got to fix that as well. So what's next? I'm going to create a proper type system for Ale, and I don't mean a proper type system as far as how Go works, because I think that type system is good, but I want to create what's called a Hindley-Milner type inferencing system for the language itself, so that you can get valuable information about whether or not you violate type compositions. Like adding a number to a string in Lisp is invalid, but it's a runtime error unless you have type checking at compile time. And so that's the next thing that I would do. I'll be adding a foreign function interface at some point. I had one at the beginning, but I didn't like the design, so I threw it away. And then, of course, performance improvements. Or maybe I won't do any of that stuff, because for me, this is my first Go project. And the real goal of that was to learn how to properly code in Go. And I think I mostly did that. And so the project itself has kind of served its purpose. I never meant to create a Lisp environment that the entire world was going to use. So I'm not Rich Hickey in that sense. I really just wanted to learn something. And so the next language I learn, I'll do exactly the same thing. I'll just go and I'll build something big so that I can get really deep and in a lot of pain with whatever language or framework that happens to be. Because that's for me, the amount of pain that I experience is a good heuristic measure of how much I'm actually learning. So that's it. Any questions? And now I can drink water too. What is a macro? Are you familiar with C? So C has a macro system, but it's not anywhere near as good as Lisp's. So the idea of a macro in Lisp is that it's actually just a Lisp function that's been tagged as being a macro. And the useful thing about it is it will take data structures and transform them into new data structures. And so that you can do like macro expansion. I can show you really quickly some of the macros that I've written. But the important thing about them is that they happen at compile time. So by the time you create this intermediate code, there are no macros in your code anymore. It's all sort of the basic primitives of the language that it's been sort of boiled down to. The macros do a lot of sort of interesting work. Let me pull up some code real quick. Yeah, basically, but with added zest, I would say. Let's see if I can find some. By the way, this is the nastiest function I ever wrote. This is the abstract machine, and it's huge. So I'm going to look for some macros. I want to find one that's particularly simple. Okay, yeah, so this is a good one. I don't know if can you see that? I assume so because I'm sharing the screen. So this is creating a macro called when. Right? And this is actually extending the language. So you're creating basically a new language feature called when. And what it's doing is it's taking 3 permutations of arguments. The first one is that you give it just a single value, and it basically returns an empty list in that case because it can't treat it as a conditional. It's just going to say, I can't do anything with that because you aren't telling me what to do with it. The second permutation is you perform some conditional test. If it is true, then you actually return the second argument. And in this case, it's emitting new code. So the macro is actually producing code that is now an if statement with test and form, and then an empty list as the else branch. Same thing for this third permutation. If you give it a conditional and then you give it a rest argument, so this is like a spread operator, the dot. It's basically saying, give me the rest of the list. So if it's more than one thing, I want to do something special in that case. And it's emitting an if, let's call it an if function, because if is a function in Lisp. It doesn't, it's not a statement because there are no statements in Lisp. It's going to basically create a block and run all of those forms if the condition is true, but otherwise return an empty list if the condition is not true. So this is effectively what a macro is doing. When you say something like, when true, print line hello, what you're really telling it to do is create code that gets compiled like this. Not that this is a good example because it's just very basic, but it would look something like that. So print line hello, which actually returns nil in Lisp, well, at least in my implementation of it, or return an empty list, basically. So I hope that kind of gives you an idea. So the answer, the question from Craig is, how do you keep motivation? Like I said, the approach that I take is always to start really small and then build incrementally. I never try to sit down and do one big, massive design from the beginning, because the problem with big upfront design is that the end result never matches your imagination for it. Better to have a goal in mind and then constantly create small increments toward that goal and keep checking yourself to make sure that you're still actually converging toward that goal rather than going completely off into the weeds. So it's actually easy to keep that motivation. And then everything I learned about the language actually reinvigorates me about the language itself. The question from Anderson is, how long did it take to build it to the point where you were happy with the result? I was happy with the initial lexer. I mean, it didn't do anything. I think by the time I had an interpreter where I could probably execute about 80% of the language, I was pretty satisfied with it. I could have called it a day there. But the one thing that sort of compelled me is that I hadn't really gone into building optimizers at that point. I had done a little bit in code that generated JavaScript, but never anything in functional language. And that was kind of the thing that drove me, is that functional languages come with a whole different set of requirements for how you optimize code that most imperative languages don't require you to deal with. Did I miss any of the questions? They were scrolling by, but.
I think
No,
you got
good.
all the questions.
Cool. And if you have any more questions, you can just reach out to me on Twitter. I'll probably be there for the next month.
Great.
Cool. So I'll just stop sharing my screen now.
Thank you very much.
Thank you.
The recording of the talk is going to our YouTube channel, as always. And I guess now is time for the announcements and the round of applause. If anybody wants to unmute themselves and make a round of applause, please do this.